Hello, fam. This is Zekaya from Mathatainment, reminding you that enthusiasm implies excellence. We are still building on our lessons on algebra, and today we are going to look at the type or the nature of roots. Why are we studying the nature of roots? You may remember from our previous lesson, we learned how to solve quadratic equation using completing the square. And from that, we managed to prove a very powerful formula here. Given an equation of the form ax squared plus bx plus c, where a, b, and c are real numbers and a is different from 0, the roots or the solutions of this equation are given by this formula here, which is famously known as the quadratic formula. We proved this formula in our previous lesson. By looking at that formula, we are a bit sensitive when we look at some of its parts. For instance, if we look at the denominator there, we may be worried whether the denominator is equal to 0 or not, because we know that that will ruin our solutions. However, the denominator there is harmless because we are sure that a is different from 0. That's what we are told from the definition of a quadratic equation itself. So if a is different from 0, then 2a is also different from 0. So now the only part that may be scary is the part under the square root. Why is this the part under the square root? Well, I'm going to find square root of random positive values here and see if I get a real number as an output. Let me start with the square root of 1, for example. I'm getting something which is a real number. Square root of 4, I'm getting an output which is a real number. Square root of 100, I'm getting an output which is a real number. Now, what about square root of -1? I'm no longer getting a real number. Maybe I was unfortunate because it's just -1. Let me try square root of -1000. I'm not getting a real number again. It looks like I can only get a real number if that part under the square root is non-negative. It looks like the part under the square root hates being negative. The moment you set it to be negative, then it becomes stingy with the real numbers. That part under the square root therefore has a special name, and we call it the discriminant. We call it the discriminant, and is denoted by capital letter delta, which is given by b squared minus 4ac. The existence of our real root depends entirely on this quantity under the square root, which we call the discriminant. So we have to respect this part under the square root. That's why I'm going to talk more about this part under the square root here. We said this part is called the discriminant. So when we have the discriminant, there are two possibilities. It's either my discriminant is non-negative, meaning it's greater than or equal to 0, or my discriminant is strictly negative, meaning it's less than 0. If the discriminant is non-negative, then my roots are real. I'm going to get real roots there. But if the discriminant is strictly negative, then you're going to get non-real roots. You won't get real roots, you are going to get non-real roots. The roots are there, but they are non-real. Our calculators, unfortunately, are programmed in the set of real numbers. Hence, when you punch a square root of -1, you get math error. It doesn't mean that the roots are not there. They are there, but they exist in the set of complex numbers. Now, let's move forward. Now, when your discriminant is greater than or equal to 0, or when you have real roots, you have two more possibilities there. You have two more possibilities. It can happen that your discriminant is strictly greater than 0, or your discriminant is exactly equal to 0. If your discriminant is strictly greater than 0, then in addition to your roots being real, they are also unequal. And in addition to your discriminant being greater than 0, like I said, you know that your roots are already real. And in addition to that, they are unequal. Now, another possibility is that your discriminant can be exactly equal to 0. If that is the case, then you know that your roots are equal. That is in addition to them being real. They are also equal. Now, if your discriminant is greater than 0, it can happen that the value of your discriminant is something very interesting. If your discriminant is greater than 0, it can happen that the value of your discriminant is something very interesting. It can happen that the value of your discriminant is a perfect square. If this is the case, well then this is interesting because in addition to your roots being real and unequal, they are also rational. They are also rational. So now, that's a very nice diagram there. To start, I'm going to repeat explaining this again. You have your discriminant. It can either be non-negative, which is greater than or equal to 0, or it can be negative, which is less than 0. If it's non-negative, then you have real roots, you know that. If it's negative, you have non-real roots. Now, in addition to being greater than or equal to 0, it can either be strictly positive, in which case you have unequal roots, and if the discriminant is exactly equal to 0, then you have equal roots. Now, in addition to your discriminant being positive, it may happen that it gives us a perfect square. Then in addition to our roots being real and unequal, they are also rational. Now we are in the right position to look at examples. The first example says, we want to discuss the nature of roots of the equation 2x squared minus x minus 1 equal to 0. Well, that equation is already in the standard form of a quadratic equation because you can easily see that a, which is the coefficient of x squared, there is 2, b, which is the coefficient of x, is negative 1, and c, which is a constant term, is negative 1 again. Therefore, we can find our discriminant as follows. Our discriminant is given by b squared minus 4ac. So, for b squared, we have negative 1 all squared minus 4 times 2 times negative 1. So, what do you get there? We are getting a 1 plus 8. We are getting a 1 plus 8, and that gives us 9. Now, let's talk about this. You can see that 9 is greater than or equal to 0. That confirms that your roots are real. Specifically, in addition to that, 9 is actually strictly greater than 0. It confirms that in addition to our roots being real, they are also unequal. And now you see that 9 can be written as 3 squared. So 9 is a perfect square. So in addition to our roots being real and unequal, they are also rational. Therefore, you know that the roots are real, unequal, and rational. That is your conclusion there by looking at what you got from your discriminant. Let's look at the second example. Here we are required to determine the value of k for which the equation 3x squared plus 2x minus k plus 1 equal to 0 will have real roots. Okay, that equation is already in the standard form of a quadratic equation because there you can see that your a is equal to 3, your b is equal to 2, and your c is equal to negative k plus 1. So now, let's try and find our discriminant. Let's find our discriminant here. Our discriminant is given by b squared minus 4ac. And in this case, our b squared would be 2 squared minus 4 times 3 times negative k plus 1. So here, 2 squared is 4 minus 12 into negative k plus 1, step by step. So I have 4 plus 12k when I remove that bracket, minus 12. So this gives me 12k minus 8, because 4 minus 12, that gives us minus 8. Well, we want our discriminant to be greater than or equal to 0. That is, in order to have real roots. In order to have real roots, our discriminant must be greater than or equal to 0. Therefore, this implies that we can set our 12k minus 8 to be greater than or equal to 0. Now, that's a linear inequality. We can simply solve for k there. 12k is greater than or equal to 8. And now we divide by 12 on both sides. And then we have k being greater than or equal to 2 over 3, because 8 over 12 is the same as 2 over 3. So that is the value of k for which our given equation there will have real roots. Right, now let's look at the next example. Here, we are required to show that the roots of this equation, which is x plus m multiplied by x plus n equal to 3p squared, are real for all real values of m, n, and p. How do we do this here? We're going to write that equation into its standard form first. So we'll have x plus m multiplied by x plus n equal to 3p squared. So let's carefully remove that bracket. So we are going to have x multiplied by x. What do we get there? We are getting x squared. And then x multiplied by n, we're going to do it slowly so that everyone will follow. We're going to get xn. And then now we have m multiplied by x, and that gives us xm. And then now we are going to have m multiplied by n, and that gives us mn. And this is equal to 3p squared. So what do we have there? We can have x squared plus, and I can write n plus m all multiplied by x, taking x out as a common factor. And then I have plus mn minus 3p squared equal to 0. Now I have a quadratic equation there. As you can see that our a there is precisely 1, and our b, which is the coefficient of x, is n plus m, and our c, which is the constant term, is mn minus 3p squared. That's what I have. Now I will find the discriminant there. Let's find the discriminant there. The discriminant, which is given by b squared minus 4ac, it will be n plus m all squared minus 4. Our a is 1, and our c is mn minus 3p squared. So this gives us, if I'm expanding that bracket, I will have n squared plus 2mn plus m squared minus 4mn plus 12p squared. So this gives us n squared 2mn minus 4mn. These are like terms. These are like terms. And they give minus 2mn. I have plus m squared plus 12p squared. So I can also factorize this quantity here. The first three terms there, I can factorize them. How to factorize them? They are the same as n minus m plus 12p squared, which you can write as n minus m all squared plus 12p squared. Now, you're going to need a bit of some reasoning here. You will reason a bit here. Now, here, we are told that m, n, and p are real numbers. M, n, and p are real numbers. And the property of real numbers is that the sum or the difference of real numbers is a real number. And another special property is that the square of any real number is non-negative. So you see here, that quantity within the bracket, this quantity here, we know that it is a real number because it's just a difference of two real numbers. Therefore, its square, the square of that real number, we know that it's greater than or equal to 0. It should be non-negative. Similarly, p is a real number. Therefore, p squared is also a real number, which is non-negative. and 12 times p squared is also a non-negative real number. This means that we are actually summing up two non-negative real numbers. That's why we are going to get a non-negative real number. So there we have greater than or equal to 0. This confirms that the roots of this equation are real. No matter what values of n, m, and p are, the roots of this equation will always be real, because you can see that we have proved that the discriminant is always greater than or equal to 0. That's what was required from us here. Let's look at the next example. Here we are required to show that the roots of the equation 2x squared minus kx plus x plus k minus 3 equal to 0 are rational for all real values of k. Right, here, let us take that equation and write it in its standard form. We can write it like this. We have 2x squared plus, then I have minus k plus 1 all multiplied by x plus k minus 3 equal to 0. That is its standard form. From there, you can see that the coefficient of x squared, which is a, is 2. The coefficient of x, which is b, is actually negative k plus 1. And the constant term is actually k minus 3. So from there, let's try and find our discriminant then. Our discriminant is given by b squared minus 4ac. What is our discriminant? If we know it's given by b squared minus 4ac, we already know a, b, and c. Our b is negative k plus 1. So we have negative k plus 1 whole squared minus 4 times 2 times k minus 3, which is our c. Let's carefully remove that bracket. Negative k squared, that is precisely k squared. Negative k times 1, that is negative k times 2, that is negative 2k. 1 squared, that is 1. Minus, I have 8 times k, that is minus 8k. Minus 8 times minus 3, that is plus 24. That's what I have. So it means there I will have k squared minus 2k minus 8k, that is minus 10k. And 1 plus 24 gives me 25. Now, on the right-hand side there, we have a trinomial. So we can factorize that trinomial using a trial and error method, and you will see that the factors are k minus 5, k minus 5. Those are the factors. And since they are the same, you can take one factor and square it. You can have k minus 5 all squared. Well, now, we are told that k is a real number, and 5 is definitely a real number. So the difference, k minus 5, is also a real number, and therefore, the square of that difference, we know that is greater than or equal to 0, because the square of any real number is non-negative. So this confirms two things. We know that k minus 5 all squared is non-negative, meaning we do get real roots. And k minus 5 all squared, it means that k minus 5 all squared is also a perfect square. It is a perfect square. So now this is enough to confirm that the roots are rational for all real values of k. The roots are rational for all real values of k. So now I'm leaving you guys with your problem to try. This is yours to try. We are required to determine the value of k for which the equation 4x squared minus 2x minus 12x plus k plus 13 equal to 0 will have real roots. You want to determine the values of k for which, or the value of k for which the equation 4x squared minus 12x plus k plus 13 equal to 0 will have real roots. Please incorporate everything that we did today, starting from that diagram of the discriminant, and check all the possibilities and what do you require the discriminant to be in order for you to have real roots in your equation? So thank you guys. We are going to meet again in the next video. You are on Math Attainment. Thank you.